Welcome to Power System Protection Lectures. I'm Pratap Mysore. Today we will cover breaker failure protection, which is a protection function, and also the system restoration using auto-reclosing. So far we covered only protection aspects of isolating and clearing faulted sections, and then auto-reclosing covers where we restore the system as soon as possible, or if at all, if it is feasible. So if you look at the breaker failure protection, if there is a fault on the transmission line here in this figure, the breaker detects that there is a fault and provides a signal to open the breaker. A breaker failure protection monitors this trip and sees whether it isolated the fault, and if it doesn't, it opens all other breakers that is feeding this fault. So if breaker here, which is marked red here, it fails, then all the breakers connected to that particular bus is opened out if these are sources. So a breaker failure protection essentially provides a local backup. So you have two sets of relaying you're using, primary and secondary, and if the breaker fails, it is detected and then it trips all the adjacent breakers, disconnecting all the fault current sources. So what are the modes of why the breaker fails? It can be a failed open circuit, open or shorted trip coil, could be the one, or it could be a failed link. It has dropped off, so that could be there. Or failed to clear the fault, or load, arc is not extinguished and the current continues to flow. That is also a situation for breaker failure. Or if it is an open contact, there could be a flashover across the contact when the breaker is open. These are different failure modes of this. And what we do here is we use a breaker failure input, overcurrent relay as one of the breaker failure inputs. We monitor the current, and if a signal is given to open the breaker, if the current doesn't go away, then we know that there is a failure. And then we also start a timer when the breaker failure is initiated, and then that timer allows the main breaker to operate. Suppose if it is a 3-cycle breaker, we give 3 cycles plus some margin. It could be 7 or 6, or it could be higher. You give additional margin. If it breaker current does not go to 0 within this time, then we take corrective action to you open all the breakers. Sometimes the current may not be sufficient, so we use the auxiliary contact of the breaker as a part of this breaker failure protection input. So if you look at it, if the fault occurs at time t equals 0, the relay operates, it takes 1 to 2 cycles here. And then the breaker is taking about 2 to 3 cycles. And then as soon as the relay picks up and then gives the relay that tells the breaker failure relay, hey, I sent a trips command here. The timer starts with the current, either it is supervised by the current or the timer can start as soon as the breaker failure is initiated. There are 2 levels. And then the breaker opens here and the overcurrent relay resets. And then because the overcurrent resets here, the breaker failure output will not come. And here is the margin between the breaker failure time and the actual opening time here. The actual opening time of the breaker after the fault occurred is relay operating time plus breaker time plus the overcurrent reset time. And then based on then we provide an extra margin to give a 62 breaker failure time. 62 is just a nomenclature, IEEE nomenclature for timer here. Here we have local interrupting. Auxiliary contact operates and operates all the breakers locally, which are adjacent to this failed breaker. And then if you are using a transfer trip to send a signal to the remote end of the breaker to say, hey, this breaker failed to operate, you open, then you have some time for transfer trip communication. And then this is the remote breaker fail interrupting time. So if it is 3 cycles here, 1 cycle for the relay to operate, and 1 cycle is for the relay to reset, 3 plus 1 plus 4, 5 cycles is the minimum time the relay takes. And then you are providing some margin for the breaker failure time. So this is a simple chart. I explained it very fast. Please go through this and understand how these relays are set. There are different protection schemes that are used. We use overcurrent through the break current, monitor the current through the breaker, and then we look whether we got a breaker failure initiate. These are essentially another contact from the protective relay telling that it sent a trip command to the breaker. And you AND both of them, and then as long as the current is there, then you start the timer and you get an output. But even 1.5 breaker schemes or a ring bus, the current on one particular breaker might be less than the other. So sometimes they just start the timer with the initiate and then allow the other breakers to open. And then if the current is there after the end of the timer, then you check for the current and then operate, provide a breaker failure output. These are very common things. Sometimes they assume that there are if there are dual trip coils, if one trip coil failed, then you start another timer, and then after 3 to 4 cycles, you provide another second retrip, second trip command to both the trip coils to see whether it operates or not. So if there is a mechanical linkage, then it doesn't happen. But if the one relay has failed to operate, then it uses this scheme to trip the other trip coil also to see whether it operates faster. So you have overcurrent and breaker failure starting a timer, or just to initiate starting a timer and then checking at the end of the timing for the current still through the relay, or we can and also there is a retrip. In certain cases where the current may not be sufficient, this is very common on generators which are on turning gear. If there is a fault and there is not much current, or some faults in the generator does not produce currents higher than the load currents. So under such conditions, we use the 52A contact, the breaker status. Also, if the breaker was closed, then either the overcurrent is higher than the set value, or if the breaker is closed, we allow the breaker to trip. And in SF6 breakers, we know that if the pressure of the SF6 is below a certain value, then we don't allow. Then the breaker will get blocked. So it's block, close, and trip for SF6 breakers. So under such conditions, if we know that there is a low gas, we can bypass the breaker failure timer and trip it faster right away without any time delay. So these are some of the schemes which are used, and there is sometimes they use a control timer. If the breaker failure initiate is permanently on, after some time, if this could be something wrong with the breaker failure initiate timer, you disable the breaker failure scheme. These are various variations which are available in the breaker failure. Essentially, you monitor the breaker to see if the current flowing through the breaker goes to 0 after a certain set time delay. That is the basic essence of breaker failure schemes. If there is a stability critical system, then you look at 2 out of 3 schemes, or voting schemes are used. Or for a single line to ground fault, you know that it is not a stability situation, then you can use a slower timer. If it is a 3-phase or face-to-face fault, you look at 2 out of 3. For a multi-phase fault, it can set less margin with a faster timer. So setting considerations for the overcurrents is very important in this. If you have they normally set 3-phase overcurrent elements and then 1 ground overcurrent element, and then it has to operate for all the faults. Overcurrent settings, it has to know that, or at least it should be set greater than the load current. You don't want it to generally operate, which may not be possible in most of the cases, but if it is possible, it is normally set than the highest load current going out. The only exception to this is capacitor banks. We just want to see whether the bank is connected to the system or not. So we use 50% of the rated current. The reason for this is in externally fused bank, the current goes down as the fuse blows. So the impedance increases. So the current can be less than the full load current. That's why the IEEE standard C3799 recommends 50% of the rated current as a set value. The other criteria is the overcurrent element pickup setting is always set more sensitive than the initiating relay. If there is an initiating relay which has a current sensitivity of 1 ampere, you have to set this relay also to at least 1 ampere or less than this. It cannot exceed 1 ampere. You don't want an initiating relay picking up and tripping the breaker and then giving a command and this overcurrent element blocking the breaker failure function. And then, as I mentioned, in generators and all, we use auxiliary contacts of the breakers, where if the relay cannot be set sensitive enough, overcurrent element cannot be set sensitive enough. Other criteria is the breaker failure overcurrent element has to have a fast reset time. There are some relays, legacy relays, where if the current exceeded some value, it took 1.5 to 2 cycles. What it does is it adds to your margin, so you cannot set much more less. You cannot set the breaker failure time to less than your relay operating time plus the breaker operating time plus the overcurrent element reset time. So sometimes if you have a good overcurrent element which can have a fast reset, it allows us to reduce the margin. All protective relays that trip the breaker will initiate the breaker failure. The only exception to this is the breaker failure relay operates all adjacent breakers. You don't go back and initiate a breaker failure on all adjacent breakers. We assume that there is one breaker which has failed, and and then if others fail, it is a low probability event, and we just take one consideration. So a breaker failure relay will not initiate another breaker failure. When it trips adjacent breakers, it will not initiate the breaker failure of that particular element. So this is a brief introduction to most of the breaker failure schemes. It is a very simple method. You have to make sure that the overcurrent element has to be set sensitive, and also you have to make sure that the overcurrent element cannot be set. You use contacts, auxiliary contacts for that, and then there is enough margin to cover the total reset time, including the operating time, including the reset time of the overcurrent elements that are used in the relay. So now, if you look at the types of faults in the system, most of the overhead lines, most of the faults are temporary. Over 70% of them are transient in nature. Most of them are line to ground faults. So if that is the case, why don't we just try to go back and restore the system as soon as possible? So one of the systems that are used is the advantage of this is you can close the breaker back, restore the system, and then restore power to the loads. So there are 3 types of classifications on reclosing. One is the high-speed reclosing, one is time-delayed reclosing, and then the other one is single-phase reclosing. High-speed reclosing is used if both ends of a line trip simultaneously. If we are using pilot schemes where we exchange information so that both the breakers on a transmission line with 2-terminal transmission line detect the faults at the same time and open at the same time, then you know that the line is completely de-energized. It is reclosed pretty fast. So if there are stability concerns, such restoration really helps the system to maintain the stability. But there are some cases where if it is a permanent fault, the 3-phase fault, then it might reclosing on a permanent fault is dangerous. So we disable high-speed reclosing for a 3-phase fault, or disable reclosing completely for a 3-phase fault. The delay of reclosing is set longer than the deionization time in the high-speed reclosing. If T is the cycles, these are empirical formula which was given in by the Westinghouse book. So the time is given as system kV divided by 34.5 plus 10.5 cycles. So if it is a 345 kV system, the minimum dead time, that is from the time the breaker is opened and that is a de-energized state, to the time it closes and energizes it, it has to have at least 20 cycles delay. Otherwise, there is a probability that ionized gases will recombine and reignite, and then it is not a successful reclose. If it is a 115 kV system, it is 10.5 plus 3, so 13.5. So this is just an empirical formula that has been used, and many utilities have come up with their own levels based on their past experience, and most of them are set very close to this. High-speed reclosing applications, again, as I mentioned, you have to have high-speed tripping at both ends. So in case of transmission lines, if you are using pilot schemes, then it is extremely important for you to make sure that the pilot is working for both ends to reclose. So if the pilot is not working, then they restore it, they disable the high-speed reclosing. And then may not be possible on tie lines due to excessive angle drift. If there are two systems which are connected on tripping of a line, the line angles could be as high as can be higher than 90 degrees, and we have seen that in some cases. So you have to look for the angle difference, and you have to make sure that reclosing does not cause any other stability issues or excessive torques on the generators. So if it may not be possible to close on high speed during such conditions. And most of the times high-speed reclosing is unsupervised because we assume the system has not drifted so far apart. Then we can check without any closing the phase angle between the line side and the brush side of a breaker, we can close it. Reclosing is unsupervised, as I mentioned it. Only at the generating stations where you have lines connected in the same row of a breaker and a half for generators, we try to use supervision to make sure that we are not closing back on that. And then, as I mentioned here, we might read switching surge studies. Equipment rating should be higher than the anticipated surges when you try to reclose for a permanent fault. That is more important for us to look at it. High-speed reclosing is blocked for three-phase faults for stability critical areas. If it is not used at substations with generators, as I mentioned previously, and it is also blocked for out-of-step conditions. If a system is severed due to out-of-step, then we don't go back, and then we disable the high-speed reclosing also. So, and also it is not used if the instantaneous tripping is not possible at both ends. On lines with protection with no pilot communications, we cannot use high-speed reclosing. So we go back and then use time delay reclosing. Typically, it is supervised by the voltage conditions because we don't reclose immediately. The systems might have drifted farther apart. So when we close, we look whether the system is okay, and if the line is dead, then we close one end, and the other end can either go back on synchro check. We look at the phase angle difference between the voltages on both sides of the breaker, and if the voltage is within certain range, we try to close back. As you say here, under voltage setting on the voltage relays is set higher than the induced voltage. Induced voltages due to some other lines can be 30 to 50%, so they are set higher than that to check for the deadline condition. And time delay tripping may get blocked if the voltage setting is lower than the induced voltage. That is why we set it like that. And typical time delay is set to about 15 seconds. 15 seconds is the duty cycle of the most of the breakers. If it opens and closes, and then you give 15 cycles before you open again. Or if you open and then you close and open intervals, you can give open, close, open is one duty cycle of a breaker. You have to wait for 15 cycles for the springs to charge, and then that is how this has been historically set to 15 cycles. It can be set lower than this to 5 seconds. Yes, you can do that if it is only one shot. If you have multiple shot reclose, then you have to have an interval of at least 15 seconds to allow the charging mechanism to restore the spring charging during reclosing. Number of recloses, they say the first reclose is most successive. It is about 83%, and then if after that the second one is about 10%, and the third one is about 1.5%. So the chances of a successful reclose decreases after the very first one. most of the transient faults, if they are transient in nature, the very first reclose will bring it back. The second and third are just additional attempts to put back the system and to restore the system. But the amount of reclosing you do, if it is a permanent fault, then you are giving a lot of bumps. And if they are voltage sensitive customers, you try to limit it to one or maximum two and not go more than that. Whereas in rural areas where you're in the distribution systems, you can set it higher, because if there are tree branches, you want to burn them out and then you want to put this back into the service, restore the loads. So more number of recloses are used in distribution network. That is also reduced if there are voltage sensitive customers. But in transmission systems, they generally use one or two. Reclosing in generating stations, there were two papers published in 1979 which analyzed the turbine shaft torque. So if a fault occurs, the generator speed up, and if you trip and then reclose, then if the fault is cleared, then the system is at synchronous speed, the generator is at a higher speed. It produces a rotational torque on the generator, which could be detrimental to that. So they say that there is a potential significant damage only for unsuccessful three-phase fault. So a lot of times successful the three-phase faults near generating stations or in the system is generally blocked, and then there is no significant damage for any successful fault, any line to ground fault, they say. And also they try to give a time interval. They don't go for instantaneous reclose near generating stations or at voltages where the generators are connected at that in a particular substation. If you have a line with power flowing, heavy power flows, if most of the faults are single line to ground faults, why to trip all the three phases has been asked many times. And then under such conditions, what we do is we just open only the faulted phase, and then you close back after a longer time delay, typically 1 second. The system remains synchronized and 2/3 of the power is still flowing on the line, and then it allows us to restore the system if it is a temporary fault. So under such conditions, we try to use shunt reactors and neutral reactors to reduce the secondary arc. That is, the arc still persists, continues due to the capacity coupling between phases. The phases, energized phases, feed the fault through the capacitor, and sometimes arc continues to flow even after the phase is de-energized. We use neutral reactors for that. So this is in short a basic concept about this. We will look at the other condition, say synchronism check. As I mentioned in time delayed reclosing, you close one end with a hot bus, a hot system and a dead line, or if the line side is more stronger and you're closing and energizing a substation, you use a hot line and dead bus. Hot line means the voltage is above about a set level, and if the voltage is below that, then line is considered to be dead, below a set under voltage setting. If the voltage is above that, it is considered to be live. So under such conditions, we use hot bus dead line or hot line dead bus, or if both sides are hot, then you disable the reclosing, time delay reclosing, and then you look for the synchronism. Both the voltages must be within certain phase angle. If the phase angle is much higher, standing voltage phase angle is much higher than some degree, when you reclose, this might produce some ripple effects, producing torque shifts on the generators. So that is checked out, and then they are around up to 40-45 degrees it is allowed. If this breaker is far away from generating stations, and one of the utilities have set it as high as 60 degrees for reclosing, because it has no impact on the generators. So in the synchronous check relay allows automatic reclosing at the other end if the voltages on both sides of the breaker are within a set voltage range, and the angular difference is within a set angle. So bus voltage, you look for hot bus and dead bus voltage settings are there on synchronism. Then line side also you have hot line and dead line voltage settings. and then the angle allowables determines the allowable slip frequency between two sides. So normally in a system that is already connected, this angle will not vary that much. Whereas at the generator, when you are synchronizing, the generator is at a different speed and then it rotates. Most of the times in a system, you get a standing angular difference in when you are looking for synchronism check. So alternate settings, whether you can look at the angle difference between the two voltages to be set, and then you allow a timer if the two voltages are within that particular angle, say plus and minus 30 degrees from one voltage reference, then for a certain amount of time, say 3 seconds, then you allow the relay to operate. If you convert this time and then the window within which these two voltages have to be within certain angle, it becomes a slip frequency. The frequency is a difference between one side of the breaker to the other side of the breaker. Sorry. Based on this, the relays are set. There are settings available either to set the slip frequency or to set the angle and the timer. And here typical settings I have seen in some of the utilities I have given that this need not be same. Here the dead voltage is above 75% of the nominal. As I mentioned, it has to be set higher than the induced voltages. So you don't want a false indication telling that the bus is live because of the induced voltages. These are set above 75%. And dead bus, maximum induced voltage is 50 to 60% is set above that. And these are typical values I've given you. You can look at it. And angular settings, I'm just taking this the window within which two voltages have to be within that particular angular window. If you look at the time, it translates to 3 seconds and then 30 degrees plus minus 30 translates to 0.055 hertz of slip frequency between the two. Some utilities have allowed 40 to 45 degrees. But as I said, in most of the system, interconnected system, which are you will have a standing angular difference between the two. And if there are two different systems with no other parallel connections, you can have a slip frequency going through that. Line restoration, most of the times we use one high speed and then one or two time delayed reclose, and then sync close reclose is there. In the time delayed reclose also there are different philosophies. Some of the companies use weak side to reclose first and then bring in the strong side with the sync to limit the damages due to the currents, because the weak source will have lower current. Whereas some other utilities where they have to pick up a lot of load, they use the stronger system to close first and then allow the weaker end to reclose to come back on sync. Then after that, the last section which we want to cover in today is auto-sectionalizing. Suppose if there are some loads on a line, and then if there is a fault here, then what happens is both the line trips, and then there are voltage detections on these both sides of this load, and they, as soon as they say that there is zero voltage, both of them open, both MODs open here, and whatever side which recloses, whatever side that recloses will energize that voltage detection, and then only that particular disconnect switch is closed. This is one of the sectionalizing schemes. In the breaker failure also, when a breaker fails, you can isolate the breaker with opening the MODs and then reclosing the rest of the breakers after that failed breaker is isolated. After breaker failure sectionalizing, I covered it, and transformer sectionalizing, if there is a fault on a tap transformer, we do the same thing. Other examples are, if you have, this is an example of auto-sectionalizing. In a ring bus, you have a transformer here. If the transformer faults, then you open both the ring breakers and then open this disconnect and close the ring. Or for a breaker failure sectionalizing, if this breaker fails, you trip all the breakers connected to the adjacent breakers, open this breaker and restore and then reclose those breakers after the time delay. So the references for this are C37102. There must be a later version, and C37119 is going through revision right now. And the one is for the auto-reclosing and one is for the breaker failure sectionalizing. Please do refer to this, and thank you for this. And then hopefully you got an idea about breaker failure, where we look at the current monitor the current going through the breaker, and when the initiate comes, we look whether the breaker is closed or the current is still flowing, and take corrective actions to open all the breakers adjacent to that particular breaker. And in the restoration schemes, we have different schemes: high speed and time delayed and sync check. We did cover that allows the system to be restored automatically without any operator intervention. Thank you.